Welcome back, everyone, to Virtual IoT and Edge Days 2022. This is our last session, last but not least, because I think we've got a very interesting topic here. Our presentation will be on MQTT over QUIC, which is something I didn't know you could do. So looking forward to learn about the details there. So our speaker, William Yang, is a software developer with EMQ Technologies. And if you're ready, up to you, William.
Okay, thank you, Frederick. I guess you can see my screen. Hi, everyone. My name is William, and I work at EMQ. Today we talk about MQTT over QUIC, the opportunities and challenges. First, short introduction about our EMQX. EMQX is a open source MQTT broker written in Erlang. Yeah. Okay. Oops. Okay. In this talk, I will cover 3 topics. First, I will give you some introduction about QUIC protocols, and some history, some functions, and some cool features it provides. And then I will talk about the opportunity for IoT if we use QUIC as the transport, and also give you some information about our proof of concept. Last, I will share some information regarding the challenges when we met when we are developing the proof of concept. Okay, so first, what is QUIC? QUIC is the new transport protocol built for today's modern web, HTTP3. And actually, HTTP3 is mostly about HTTP to QUIC mapping. QUIC is UDP based, but it is connection oriented and provides end-to-end encryption. It also supports multiplexing with streams in the same connection, and flow controls and some other cool features. So who use QUIC? Here I just give you some example. As you can see, most of the big players or internet service providers, they already put QUIC in use in production. And also we have a bunch of QUIC libraries you can develop with. Okay, where QUIC is used. So probably 3 parts. Mostly QUIC is used in CDN, edge network. I think this fits our conference, edge network. Secondary, QUIC is also used in client to server communication. And the last part, QUIC is not that used in server to server communication. So some history, 2 terms, GQuic and IETF QUIC. GQuic is originally developed by Google since 2014, and it's mainly for Chrome and the Google service communication. So Chrome browser talks to Google service over QUIC, such like YouTube or something. And in 2016, it already taken 7% of internet traffic. Then in the same year, Google bought it to IETF, try to standardize it and modularize it. So IETF is kind of global standardized protocol, and this is the one I'm talking about. And before GQuic, there are lots of attempts to improve the transport layer. Some of them now they are in use widely. Some of them not in use, or some of them they are just used in specific industries such as SCTP in telecom. And also there are some improvements or workaround on the layer above transport to provide the stream multiplexing and flow control, which indeed are functions that should be provided by transport. So what I list here is that QUIC protocol. It's not built from scratch. It's learned from the previous experiences. That also makes QUIC protocol a little bit complex. So why do we need QUIC? In another conference, not IoT related, I got a question like, why do we need a new protocol, new transport? Why can't we just use SCTP? I will tell you why. Yeah. So before we go to that part, let's just revisit HTTP2. So on top of the IP, we have TCP. And TCP layer is connection-oriented, reliable transport that ensures ordered bytes delivery. It also provides congestion control and loss recovery. Then we have TLS layer, and TLS provides trusted encrypted session for application layer. So nowadays, data is privacy, so encryption is kind of mandatory for modern web. Then the most interesting part is the HTTP2. The HTTP2 compares to HTTP. It provides string multiplexing in one session or connection, so that the browser could fetch a remote resource such as HTML, CSS, or JavaScript in parallel. Then when you have this multi-string, then you need priorities. So for example, when the browser is fetching the image for display, it prioritizes fetching the in-screen image of the over the off-screen image, because the off-screen image is only needed while users scroll down the page. Flow control is another necessary consequence of using multiplexing. If the receiver is not able to process the incoming message as fast as the sender is sending, it will build a backlog, and eventually it will become buffering, package drop, or retransmit. Such is a big waste. So it works well. Then still we have some shortcomings. For example, the congestion control in TCP is not very nice. So what prevents us to be more get more evolutions? That is the middle box. In QUIC, this middle box is very a famous problem that it's trying to get rid of. Middle box. What is middle box? Middle box likes to do some small things, and but they don't know what is the up layer is doing. And some of the middle boxes, they are just actually transport endpoints. So when you think you are talking to the server directly, but you are like load balancing in the middle, and there are two TCP connections. And there are many middle boxes, and you can't have control, and when you try to update, for example, TCP stack in these middle boxes or adding new features, it's tough, and you can't just do it. And for the middle boxes, they are like NAT routers for do address translation, because we have limited address space in IPv4, and we have firewalls to those access control and security, and load balancer, and there are more. So what about IoT? Do we have the same problem? I think so. So that is why QUIC is built on top of UDP. So QUIC runs on just this existing protocol UDP that everyone already supported. This minimizes the requirements to run QUIC on existing simple protocol. You don't need to bring up new protocol or new devices to support it. And then QUIC just do end-to-end encryption, which means leave minimal information unencrypted in UDP or on wire, so that it will not be interceptable by middlebox, and hope middlebox can do nothing on it. And the QUIC supports all the features I just talk about in HTTP2, and especially it brings the multiplexing or multi-streams down from the application layer to the transport layer. As we said, it is the transport layer's job. So opportunities for IoT when we use QUIC, what's the benefit? First, it's the QUIC can reduce the security handshake latency with something called 1RTT. Let's just talk about how the old way and the TLS 1.2 do handshake. So with TLS 1.2, client and server, they first need to do TCP handshake. After TCP handshake is done, it's try to do the do the TLS handshake, and I draw the red dots there. They are the blocking point, which means the endpoints have to wait for the response from another side. It cannot proceed without the response. So this is kind of a round trip or wasted. Yeah, after the TLS handshake is done, it can start to exchange application data. So with TLS 1.2, you can see there are 3 red dots and 3 round trip. So what is QUIC 1RTT? That is just simple. QUIC only need 1 round trip to finish the handshake, and you can see it's only 1 red dot. This is because QUIC is over UDP. You don't need to do a connection handshake. And also in QUIC, both client and server, they are smart enough to get to the best guess on what will be the quick how to say what would be the key exchange algorithm. Yeah, so the client do not need to wait for the server to select the algorithm. That is why it's so quick. Yeah, the second is my favorite part about QUIC. That is, it can reduce reconnect overhead or just reduce the number of reconnects. So let's talk about what is reconnect problem. Reconnect is very common. For example, the client stays in RUSI network. For example, some fast-moving objects, trains or vehicles. And some clients, they are just switching network. The network address will be changed, like IP address will be changed. For example, you are moving out, or you walk out of your home, and you change from Wi-Fi to 4G, and when you back, it's another direction. And also some clients or some sensor, they can be mostly sleeping. Then it will become some idle timeout, and especially if it's behind the NAT, then you have NAT binding timeout, which means the port is changed, although the IP address is not changed. And the last one is server side or network side maintenance. This is, I think, we can't avoid it because we need to deploy new features, patching, security patching, and it can cause massive reconnects. So reconnect is expensive because handshake is slow and it use lots of bandwidth for TLS if you use TLS. So it's expensive on the transport, but it's also very expensive on the application layer because when the client is connected or disconnected, it's also shifting the status in the application layer. If you have a load balancer in front, then probably the next connect will end up to another server. Then yeah, there will be a lot of overhead there to take over the session or something. Yeah, so the biggest problem, I think, is for the reconnects in IoT could become DDoS. Image that we have a service like this one, so connecting 100 million clients with 100 million connections. And what if you need to do some server maintenance? Then even just 1% of the connection need to be reestablished. It's like 1 million reconnects, which is huge. So how QUIC solve it? I think there are two parts. The first is zero RTT. Here I think I just show you this part is one RTT that before client and server, they don't know each other. They do one RTT handshake. And once the handshake is done, application data is exchanging, then the server can send a new session ticket to the client. And the client just remember the session ticket for re-entering, and this is re-entering ticket. So if something happens with this connection, disconnected or idle timeout, then, sorry, client can just use this session ticket to establish a new connection without waiting for the server part. And also, as you can see, the application data can be exchanged in the first packet called early data. This is very nice. And this is called a connection resume in QUIC. Although it looks like a connection resume, but in QUIC it's a new connection, but with session ticket. The second thing QUIC can mitigate the reconnect is to just reduce the number of reconnects. So in the feature is called connection migration. So in TCP and UDP, we use 5 tuples, or someone called the 4 elements tuples to identify the pair. So if one of the elements is changed, for example, the port or the address is changed, then you have to do reconnect. But in QUIC use connection ID to identify the connection. So as long as connection ID as long as connection ID is kept, then server clients, they know each other. They don't need to redo the handshake. So here is an example on the right side. You can see that client connect to the server through access network, Wi-Fi access network, and with connection ID and with this source IP address. But client can do network path probing with, like, for example, 4G network. That's just keeping the probing and verify the path works and that the MTU fits the needs. The MTU size fits the needs. Yeah, and once there are some conditions, or you get worse coverage for Wi-Fi, then you can just migrate to 4G network. You can see the source address of the client is changed, but the connection ID is not changed. So we call it active migrate. That is, the client knows I can use this new path. Yeah. So let's talk about the next one, multiplexing. So what does that mean? So with multiplexing or multi-stream, as we talk about in HTTP2, you can run things in parallel. And once you can do this kind of thing, then you can cancel request, and also you can do server push. And most important, I think it also solves the header of line blocking issue. Most of TCP-based protocol has this kind of issue. Let me explain what is head of line blocking issue. You see this in this picture. We have client and broker using this one TCP connection, and we are like sending from client. There are like three topics, but there's one ping request. In this flow. I mark them with different colors, but to TCP, TCP has no idea what are they. So TCP is kind of blinded. And if one of the packet is lost, let's say it's from topic 1, then it blocks all the connection, all the data. It blocks all the data. Then those data from like topic 2, they cannot overrun. Before I talk to how how QUIC solve the issue, I want to talk about this, how QUIC do packetization. First, outer box, you have UDP packets. Then in UDP packet, you can have QUIC packet, one or more. And let's focus on the first QUIC packet. We have headers, packet number 10. Then in this packet, you can have multiple frames. Yeah, you see the yellow and the green one. They are the application data frame or string frame for two different streams. And with QUIC streams, as you see, the QUIC streams can run in parallel, and they can be unidirectional or bidirectional streams. And the bytes or the ordering is guaranteed in one stream. So stream data, different data from different stream, they can overrun, but you can't. But the order should be kept in one string. And also you can do flow control on both string level and connection level. In this example, if let's say we have packet number 2 and packet number 3 in one QUIC packet, packet number 100, and it gets lost. Sorry. Then the data for the string for topic 1, topic 2 gets blocked, but not for the string which carries the ping request and the topic 4. Yeah, yes, and nowadays internet providers, they care about quality of experience and sort of, or call it end-to-end experience, like video buffering or something like audio, like can you hear me? Yeah, this kind of thing. And there will be lots of new features on application side, and vendors, they just want to fast iteration on planning, deploying, developing, and deploying the new features. You cannot get fast iteration with traditional transport that runs in kernel space. So QUIC runs in the user space instead. And that is why before the RFC of QUIC is finalized, the QUIC is from those big players. They already put it in production. So QUIC brings us agility. Okay, let's move on to the next part, MQTT over QUIC. So for who don't know what is MQTT, MQTT is a lightweight and efficient protocol for IoT, and it runs pub-sub communication model. In this picture, I show you in the middle, we have MQTT broker, and left side, we have sensor. And the right side, we have subscribers, like backend server or mobile devices, and they are the MQTT clients. And the right side, those subscribers, they subscribe to the topic temperature. And the left side, the MQTT client sensor, it can just publish the temperature to the broker. Then broker will publish it to the subscribers. This is kind of how it works. And yeah, you can have multiple topics. Yeah, just very simple introduction. Okay, then what type of transport is required for MQTT? In MQTT 5.0 spec, you find this. It's supposed to run over TCP/IP, but it can also run with the other network protocols that provides ordered, lossless, bidirectional connections. I think at least here, QUIC fits all the needs or meet the requirements. It's only the ordering, it's only kept in one string, not in one connection. So our proof of concept is that we have one QUIC connection between client and server, and using TLS application layer protocol name MQTT. Once the connection is established, client is required to initialize one bidirectional string in the connection to the server, so that client and server just communicate on this string, and it just works, and it works well. That is proof of concept, and then now we realize how can we make use of the features of QUIC that QUIC provides. For example, the multiplexing, multi-streams things, and there are some features we get it for free, as I mentioned before. So how do we map string of QUIC and the MQTT topic or MQTT messages? We have some ideas. So first is we can put top messages from one topic in one string, or one topic per string. And also, if the topics, they are correlated, you can also put multiple topics in one string, if the order does matter. Also, with this multi-string, you can give it different priorities. So if some topic is important than others, you can just give higher priorities. Then those topics, they will not block each other, right? And then also with these streams, we can also coexist with other protocols like HTTP3. So in one connection, you have multiple streams, some of them running MQTT, some of them running HTTP. Yeah, and with stream priorities, we can also separate a message into types. I mean, MQTT message run in parallel and gives them different priorities. For example, we can give 3 types of messages controlling, like those connect, subscribe, unsubscribe, subscribe, act, something like that. And this is for controlling. And then you can have keep alive, probably the highest priority. You put that pin in one string, and then you can have data streams. Probably you can have separate data streams for different QoS or whatever. Then it also makes that you can do something asynchronous, like if the client detect that it's the stream flow is kind of overflow or the buffer is full, but it can still try to cancel the subscription with another string. Yeah, the next thing is that flow control and pluggable congestion control. So QUIC supports pluggable congestion control, so we can develop a special one for IoT. That is one thing. Second thing is that for flow control, we can also do some innovation here, that you can make QoS 0 message to give way to QoS 1 or 2 messages because they are less important. And also, you can also use unreliable datagram to transmit real-time messages for QoS 0 messages, and those unreliable datagram is unreliable, and the order is not ensured. Yeah, that's for the opportunities and the features. Now we talk about the challenges and the limitations. First, about the network layer. QUIC has hard requirements on the network layer. For example, the MTU size is at least 1,200 bytes for UDP datagram, plus the layer 3 headers. And the fragmentation is not allowed on layer 3. It should work well mostly on internet, but it might not work in some special IoT network. And MQTT is designed to be lightweight, and many small devices are designed to send small data to save power or save the network costs. But QUIC seems to have some large network footprint due to the paddings. There are a few paddings. First is the padding in initial packet. That is when you need to establish new connection. So it needs 1,200 bytes padding. Then we also found that in some implementation of QUIC, it also have paddings for ping frame, which is for keep alive. So from time to time, you send a very big message. And also, due to QUIC is end-to-end encrypted, for encryption, you have like a minimal block for encryption, and the size of the block scales not linearly. So when you can't fit the whole size, you need to do some paddings. And yeah, and also for some security reason, QUIC sometimes padding left, padding right. I didn't look into details, but from some trace we found for example, we send a 4 bytes data, and it's end up some 100 bytes on Wireshark, in Wireshark. Yeah, and also QUIC has CPU overhead. This is because of encryption is mandatory. Also, there are some drafts try to make insecure transport, but it's not generally agreed by the IETF. So compared to TCP, QUIC has higher CPU usage, and that is not ideal for resource-constrained devices, small devices. Yeah, then about TCP fallback. Yeah, QUIC. So although QUIC is very good, but just on internet for HTTP3, there are still like small percentage, 3 to 7% QUIC attempts failed. They need to fall back to TCP due to those middle box problem, UDP is blocked, or some low bandwidth issue. The browsers, they can solve it easily, just having a 100 milliseconds delay, if I remember correctly, before the fallback. So if QUIC doesn't work well, then they use TCP. Because this 100 millisecond is not noticeable by human. But what about IoT devices? Some colleague tell me that some service, they do care about this 100 milliseconds, but some don't really care. Yeah, and also since QUIC hides everything, or not everything, sorry, most of things, and then the traditional load balancer cannot be used. You can use it, but it breaks a lot of things. Lots of features will be broken. For example, when QUIC is changing the IP addresses, then load balancer doesn't know how to do it, and it will probably make the client to reestablish the connection. But fortunately, there is a draft for QUIC load balancing. So till now, I don't see any I don't see any how to say commercial load balancing is supporting QUIC very well. And also in cloud, those like AWS AOBs, they don't support QUIC yet. Okay, the last one is QUIC protocol is complex. The large code base, because it embedded TLS 1.3, it might not fit small devices because the binary footprint is big, and also it's due to the complexity. You need to be extra care about the security, like zero RTT replay attack, and also due to the complexity, you need a very good toolings. For example, Wireshark is only for in-network packet tracing, which is not enough because most of states are just stored in endpoints, and you need them to dump the tracing messages or traces. So we need endpoint-based packet tracing. I don't know if it's feasible in IoT devices. Yeah, so conclusions, QUIC bring us much better connectivity. And we can learn from HTTP3 how to use it and how to avoid those security issues. But QUIC does not fit all the IoT devices or the networks. So we are working closely with EMQX, our products, the users of our product. Some of them, they are interested, and also OASIS to standardize it. Because we are engineers, we can't say that we know it before we can build it. Okay, so if you are interested, you can contact us. You can find us in GitHub, and yeah, questions.
So there are no questions in the chat right now, but in the audience, please add them either directly in the chat or in the questions tab. But I have questions of my own, so we are good. So from what I understand, you at EMQ Technologies implemented this particular binding of MQTT to QUIC. This is not a feature that you would find in most of the mainstream MQTT libraries that you can find in the market right now.
Right, and another group in our company, they are building SDK for MQTT over QUIC.
Okay, so the feature will be in that SDK.
Yes, it's a SDK. Yes.
Okay, so I'm curious then, what prompted your company and your colleagues to implement that? What particular problem were you trying to solve? Because I think the idea makes sense, at least in my perspective, with what I know. But I'm curious about the genesis of this idea.
Yes, we have a bunch of customers. They facing issues when those devices are in the losing network, so to say. Because mostly on those cars when they are like driving over, I don't remember the numbers, maybe 60 kilometers per hour, then the connection is unstable, and it requires it's to rebuild the TCP connection. Although we know that in telecom there are lots of optimization to improve the coverage or improve the shiftings between base station, but still the problem exists. And also we have customers, they by human made some mistake or doing some maintenance causing the reconnects, and also it becomes like a disaster so to say to them.
Yes.
Yeah, and yeah, I think those are the yeah, and also it was to mention that we also have some open source users. They contact me in person, and that they are building something that is when your car approaching to your home, then the door is automatically opening. But they have issues like the car is actually in the the middle of 4G network and the Wi-Fi network, and the time to reestablish connection or the car, the module in the car is like a switching network. It's really unstable, so to say. It's just connected, but then immediately it's try to switch network. So this is also one use case. Yeah, and due to the MQTT protocol, I think one big problem is the scalability of the broker, and like those handling those subscription is kind of very expensive, and there's lots of those clients. I think their logic is very simple. Once it's disconnected, it will just reconnect and resubscribe, and it also adds a lot of overheads on the server. As I show you, we have like 100 million connections, and if part of them they are like reconnecting, it's super expensive.
Yeah. And of course, you can alleviate to a point some of those things by using persistent sessions, and that way you don't need to resubscribe. But even then, yes, all of those handshakes and things you need to establish, it's certainly costly. Now, in a slightly different perspective, so you're doing MQTT over QUIC, and there's a different specification in the market right now, which is at Oasis, which is MQTT SN, which is essentially MQTT on the top of UDP. Now, I understand that in terms of footprint, let's say MQTT SN on UDP is the smallest, and then could we say that MQTT over QUIC is in the middle, and MQTT over TCP/IP has the biggest footprint in terms of the size of the packet and the exchanges needed? Could we rank them like that, or am I wrong there?
I think we are in the Oasis organization, and when I introduce MQTT over QUIC, and Simon, the guy who wrote most of part of MQTT SN, he really likes it, and he hope this can be used in MQTT SN instead, because
Okay.
he mentioned that if I remember correctly, he mentioned that customer, they want encryption. So because I was talking like yeah, it's sensor network, then encryption is expensive, then maybe not worth it. But he is saying like yeah, but users like encryption, and then they have like DTLs. So
Mhm.
TLS over UDP, and he told me there are lots of problems there. So they are
Yes.
really uh, finding some better solution or something. I don't know, but from my understanding, the QUIC protocol can mitigate the impact of middle boxes. That's probably the most desired features.
Okay, so we could eventually see MQTT SN over QUIC as a thing at Oasis.
Yeah, I hope so.
That would be interesting.
Because we will kind of drive this standardization, and we will see if we can bring to MQTT.
Okay, well, thank you for those details.
Okay.
So there are no further questions on my side, and I think
Okay.
that would be the end of the presentation. So thank you so much, William, for this great talk, and
Thank you.
really, I'm glad I was able to watch it, and certainly got me thinking. So thank you for sharing this with
Yeah.
us at Eclipse.
Yeah. Thank you, Frederick.